Good morning, good afternoon. Welcome to our first lesson on graphing linear equations. We're actually going to spend 2 days really emphasizing what it is to graph a linear equation because it's so important not just to be able to get the graph, but to understand what the graph is. If you can understand what the graph is, then you will be able to graph not just lines, but literally anything else that somebody asks you to graph. So the first question I have up here on the slide is the simple question, what is a graph? When you are asked to graph something, an equation, a set of points, what are you being asked to do? Specifically, we're interested in the graph of an equation. Last class, we did writing equations of lines. So given certain information about the points that are on a line, how could we come up with the graph for those points? And now we want to talk more specifically about what that graph is. I am going to, in the lesson, pause the video for a little bit to give you a chance to think about your answer to this. So here's the answer to this. What is a graph? Quick answer is, it is the picture of all the points, and by points we mean the XY points that make the equation true. And so what's really important about this, and why I think it's worth it in an Algebra 2 class to go back and talk about this, is that this definition, understanding what we are doing when we're graphing a line, it works for all equations, not just linear ones. I'll put all in big capital letters there. It works for all equations, not just lines. And that can become extremely helpful when you're asked to graph things that maybe you're not familiar with what the shape of the graph should be, or in multiple choice tests where you might be asked to match an equation with a graph. You can use this definition to eliminate answer choices and really help you do better on a multiple choice assessment. So it's important to know that this works for all equations, not just lines. So I want to establish what we mean by that, because it won't do us any good if I give you this definition here. It's the picture of the points that make the equation true, if those words don't mean anything to you. So I'm going to ask this question. Does the point 1, 5 make the equation, oops, can't quite write the equation there, y equals 2x plus 3 true? So if you are asked this question, does this point, 1, 5, make this particular equation true? The way you would determine the answer to that is you would take the x-coordinate of 1 and the y-coordinate of 5, and you're going to plug those in to the equation where you have the x and the y, and tying back into unit 1, we're going to use order of operations to simplify that, and we're looking for a true statement. So for the y, I will be plugging in a 5. For the x, I am plugging in a 1. Then we have 5 equals 2 plus 3, or 5 equals 5, and that is what is known as a true statement. So we want to interpret this. So yes, the answer to the question is yes. What does that actually mean, though? What it means is that the point 1, 5, sorry, that's really messy there. The point 1, 5 is on the graph of y equals 2x plus 3. Now, this is a little bit mathy in the way that I'm saying it. So other ways that we could say it is we could say if you graphed that equation, it would go through the point 1, 5. We can say that, like I wrote, the point 1, 5 is on the graph. And every single point that's on the graph will make the equation true. And it seems, maybe this is going to seem tedious or like a waste of time, but it is such an important concept that it's worth spending a little bit of extra time on it. So what we're going to do is take this equation and we're going to generate what the graph of this equation looks like, and we're going to do it the long way. So this is the way that you might have done it way back in, maybe even before Algebra 1, if you took pre-algebra or 7th or 8th grade math, you might have learned how to graph things this way. So give me a moment. I'm going to set some things up, and we're going to work through this. Okay, I love how I can pause that and I can take a moment and do some stuff to the screen, and for you, it's no time at all. It's wonderful. So what we're going to do here is pick values for x. And this gets into a question of what is the domain of the function. The domain really, remember from the first lesson in this unit, the domain is the set of all the possible x coordinates. So when I talk about picking an x coordinate, generally you can pick anything you want. Any number at all that's on the number line. So you can pick positive numbers, negative numbers, decimals, fractions. As long as it's on that number line for the x-axis, you're allowed to pick it. As we move forward in Algebra 2, we will have what's called a restriction on the domain, meaning that there are certain numbers we're not allowed to pick. But we're not there yet. So we're going to pick some numbers. Okay, we're going to pick a bunch of them here. We have already picked the point 1. So we know when x is equal to 1, y is equal to 5. And I'm going to come over here and plot that point. So I go right 1 and up 1, 2, 3, 4, 5. Oh, yeah, hang on a moment. Let's see if I can, there we go. This would be way better if I had a pen to do it with. So I know that the graph of this line will go through that point, but we're not restricted in picking like the number 1. So to make our graph better, we will pick some other values. So go ahead and again, you can pick anything you want. So 1 is usually a good number. I tell you, one of the best numbers to pick is 0. So typically off to the side, what you would do, you pick the number 0, is you will plug in 0 for the x. Okay, so we'll have 2 times 0 plus 3. 2 times 0 is 0, and 0 plus 3 is 3. So when x is 0, y is 3. And I'll go ahead and plot that point. 1, 2, 3. I am going to erase that scratch work. I want to show it to you, but I don't actually want it cluttering. Now, this is enough for us to graph the line. I have 2 points, remember from our last lesson, 2 points determine a line. So as long as you have 2 points, you are able to get the graph of the line. But that's not the point I'm trying to drive home with this. So we're going to keep picking some numbers. After 0 and 1, most students like to pick the number 2. So we'll go ahead and pick the number 2. And again, what we're doing here is we're plugging in 2 in place of the x. So I get y equals 4 plus 3, or y equals 7. And so I'll come over here and count 2 right. 1, 2, 3, 4, 5, 6, 7. And notice that I'm starting to reach the top of my graph there. So in order to pick some other points, I'm actually going to head in this direction. -1, often a popular point. We don't typically gravitate towards negatives, but they are there, and sometimes it's important to pick them. 2 times -1 is -2, and -2 plus 3 is 1, so we have the point -1, 1. So I will go left 1, up 1. And what hopefully you're noticing here is that there's a pattern to these points. They're not showing up all over the place on the coordinate plane. So you could probably, without going through this, predict that the next point, if I pick a -2, that it would be right about where my pointer is. So probably if I pick x is -2, I'm going to get y is -1. So let's go ahead and try that. Let's pick x is -2, and I get 2 times -2 is -4, and negative 4 plus 3 is negative 1. And I am not surprised about that at all, because that is following the pattern that we're seeing on the coordinate plane. And this is where math should make sense. It's consistent. There are patterns. So you get this one equation, and when you start plugging in the numbers, you start to see a pattern, and that pattern is unique to the type of equation you have. Now, what I want to emphasize, I'm going to do one more, or maybe two more, is that you're not restricted to the integers. We tend to shy away from fractions, but fractions work as well. So I will take, we'll do, say, the number 1/2. If x is equal to 1/2, then I will plug in 1/2 for x. 2 times 1/2 is 1, and 1 plus 3 is 4. So when x is 1/2, y is 4. So I'll have to estimate where I think the 1/2 is, and that's okay to do. We know that the 1/2 is there, and I go up 1, 2, 3, 4. And what you should notice is that that point still falls in that pattern, even though now I've picked a decimal. And you can literally pick any numbers you want, and if you filled them all in, you would end up with this consistent pattern, and that consistent pattern would happen to be a straight line. So if we wanted to pick, and there are good numbers and bad numbers, so I'm going to pick a number that kind of comes out nasty. I am going to pick the number, I don't know what I'm going to pick. We'll pick 1/3. Okay, so that would be going on the x-axis 1/3 across, and it's going to be somewhere in between the purple dot and the orange dot there. So I would plug in 2 times 1/3 plus 3. This you might want to convert to a decimal. This is going to be about 0.67, 0.3, and we end up with this kind of nasty decimal, 3.67. But if I look at where it would end up, 1/3 would be 1/3 of the way across. Well, 3.67 is going to put me right about there. And so even when you end up with these nasty decimals, you would have to estimate on the graph, but it would always, always, always follow this pattern. So there are an infinite number of points. I could make this table keep going forever, and I could go to everybody in all of my Algebra 2 classes and have you all pick a different number for x, and we'd calculate a different number for y, and it would always come out on that line. So if you think about geometry, how do we draw this? I don't really want to, I really don't want that color. Let's use this color. Draw an infinite number of points, but let's just assume for a second that I did, okay? And eventually all of that would fill in, and the way we depict that is we draw a solid line, and the solid line, remember, we shade in the points that make it true, so we're constantly shading in these points, and I put the arrows at either end to indicate that this does keep going forever. That's why it's important to have the arrows at the end of your line, because there are more points. So key takeaway from this is this: making a table like we just did, making a table always works for all equations. If you know how to do what we just did and make that table, pick an x, find a y, plot the point, pick an x, find a y, plot the point, you can graph absolutely everything. So what works for y equals 2x plus 3 is going to work no matter how ugly or messy the equation is, even if you don't understand what that equation is doing. So while this might seem tedious or kind of boring, it's also really, really powerful, because this means that with a pre-algebra level understanding of what a graph is, you can actually graph any kind of equation in the universe. And I'm not exaggerating. So we're going to look at another way, another form of the equation of a line. I'm going to show you a couple of things about constructing these tables, and then we will talk about why we don't actually want to graph lines this way, because we really don't. So let's Let's try that again. Okay, so let's consider this example here. And I'll pause to say, this is actually what's called an equation in standard form. So I think it was last class we talked about y equals mx plus b, and we said this was what's called slope-intercept form. This form where you have a number times x plus a number times y equals a number, that is what's called standard form of a line. It's sometimes it comes up in word problems, but you could use algebra and solve for y. So remember from unit 1, solve for y means get the y by itself. You could take this equation, solve it for y, get the y by itself, and you could make it look like y equals mx plus b. So just using some algebra 1 skills, what you can do is rearrange your equation. So suppose you are asked to graph this. You have this lovely tool that you can use to graph anything. Pick a number for x, plug it in, find the number for y that goes with it, and then go and plot that point. If you recognize that this is linear, then you know that 2 points determine a line, so you only need to get 2 points. If it's not linear, so if it's what we call a different family of functions, which we will study a lot of different families, then you might need more than 2 points. But the idea is that we're going to study what different graphs look like so that we can develop some shortcuts. So if you are picking points, I am always going to suggest that you pick 0. It is Miss Taylor's favorite number for a reason. So I'm going to take that 0, plug it in for the x. 2 times 0 is 0. 0 plus 3y is 3y. Divide both sides by 3, and I get y is equal to 2. So yay. We should pick another number. For x, I'm going to pick we'll pick a 1 for x. So 2 times 1, not equals, plus 3y equals 6. 2 times 1 is 2. We're going to subtract 2 from both sides, so 3y equals 4. And this time I get something not so wonderful. Now I have 4/3. That's kind of hard to graph, so I am going to put this in a decimal form, so 1.3 repeating. I can estimate where that is. My 3 is kind of bad there. Let's see if I can do my 3 a little bit better. 1.3 repeating. And lastly, I do want to show you that with a linear equation, you can choose values for y as well. You can choose values for y in other types of equations. You just are a little bit more likely to run into a problem with when you go to solve it, there's actually no solution. So it can happen. But in this case, we're okay to choose a value for y. So this time I'm going to plug in a 0 for y because it is Miss Taylor's favorite number for a reason. And so we plug in a 0 for the y. 3 times 0 is 0. 2x plus 0 is 2x. And we divide both sides by 2 and get x is equal to 3. Now we could keep going with this indefinitely. We could keep picking numbers for x and numbers for y, and we could keep filling in more and more and more points like we did over here, but we don't need to. Once we know that we're dealing with a line, whoops, where did I go? Bring it back, there we go. Once we know that we're dealing with a line, we can stop picking the points. We actually only need to pick 2. Sometimes teachers will encourage students to pick 3 just to act as that check to see if you made a mistake, because all 3 of them should line up, and if you've got them forming a triangle, you know that one of your points is wrong, and it works as a little bit of a check. So let's take a look at where these points are. The point 0, 2 would be about there. I'm going to go ahead and graph the point 3, 0, and then the point 1, 1.3 should be on this line. It should line up with the others, and yes, it's true that we have to estimate. I go right 1 and then up about 1 1/3. And there's your line. So before we wrap up this part of the lesson, I want you to take a second and think about why this is powerful. If you can master this idea, okay, we'll go all the way back to that first that first answer, what is a graph? It's a graph of all the points that make the equation true. If you haven't been sold on this, I'll do a quick example. And I'm going to look at this equation, and I'm going to look at the point 0,2. Or maybe I can do something different. I'm going off script. That's always dangerous. Okay, what I'm going to do is this. If you look at this graph over here, see this point right there where my arrow, I don't know if you guys can see where I'm trying to get my arrow to point. That point appears to be on the line. And so that would be the point 1, 2, 3, 4, 5, 6, 6, -2. So it looks like that goes through the point 6, -2. If it does, going back to that definition, the point 6, -2 should make the equation true. So I'm going to take 6 and plug it in for x. I'm going to take -2 and plug it in for y, and it should make that equation true. So 6, and then I'll plug in y is -2. 2 times 6 is 12. 3 times -2 is -6, and 12 minus 6 is 6, which is a true statement. And so because the line goes through that point, I know that that point makes the equation true. It's a very powerful idea, and you can answer so many questions. Like you guys took your baseline last week, and I don't know what's on that test, but I do know that questions that involve equations and graphs, if you get this idea, you have so much power to answer questions correctly. But we probably don't actually want to do this. So I wrote in there, here's the question. This is not an efficient way to graph. Why? Or maybe why not in this case. The word efficient balances two ideas. It balances accuracy with time. We want our math work to be accurate. None of you want to drive over a bridge that wasn't built with accurate math. You don't want a robotic surgery done where the robot wasn't designed with accurate math. But we also have time constraints. You guys have jobs, you have sports teams, you have a life and a family, and you can't spend 30 hours working on just your math work every week. So we need to have that balance between accuracy and time. This is not efficient. Why isn't it efficient? It's really accurate. Okay, I've got lots of good data points, but it's not fast. Okay, there's a couple of ideas if you've got the notes that were generated for answers. First of all, it's super time consuming to graph lines this way. None of you, and by none of you I mean me, want to create a table like that every single time we want to graph a line. We also can run into an issue where finding good numbers may be tricky. I'll put it this way. Finding good numbers to plug in. How do you know if a number is good to plug in? So in this case, like 0 was good, but 1 not so good. Over here, we had a string of good numbers. 1/2 was good, but 1/3 was not good. So how can you tell what good numbers are? Now, the reality is the more you do this, the better you'll get. You'll start to see patterns in how to pick numbers. And a third reason is it's much harder if the graph isn't a line. So when you're graphing a line, you really only need to get 2 points. But what if the graph isn't a line? There's all kinds of graphs that you've probably seen that aren't lines. How many points do you need if you want to graph something that has a curve to it? So there are some drawbacks to this. In the next lesson, we are going to explore a much easier way of graphing lines.